video session, we will discuss the memory allocations used in Linux system programming. In this session, we will be discussing the below topics such as malloc, calloc, realloc, allocate, free functions, and break and sbreak system calls. As a note, break and sbreak are system calls on which the library functions such as malloc, calloc, and realloc are built. In the previous session, we had discussed that a process allocates a dynamic memory in the heap segment. The memory allocated in the heap segment is contiguous virtual memory, and the heap memory begins after the uninitialized data segment, and the heap grows and shrinks based on the program requirement. So, whenever there is an allocation of memory, the heap grows and it shrinks when the dynamic memory allocated is freed. Now, let's discuss program break. In a dynamic memory, the heap is a place where the dynamically allocated memory is being placed. But before using heap, there is a program break which refers to the current limit of the heap. So the current limit of the heap is referred to as a program break. When dynamic memory is allocated, the program break increases. After the program break is increased, the process may access any address in the newly allocated area. We had visited similar diagram before when we discussed the virtual memory. So here we have an initialized data and uninitialized data. The memory segment after uninitialized data segment is called heap. So the start of the heap begins from this point, and initially when the program runs, there is a program break which points to the start of the heap. So whenever any dynamic memory allocation is performed, we need to advance the program break in memory location so that the memory that is advanced can be used for further dynamically allocated memory. Let's say that user needs 100 bytes of data. The program break is pushed to the required number of bytes, and after that the memory can be utilized for dynamic memory allocations. So the function calls such as malloc, calloc, and realloc internally rearranges the program break in such a way that the newly available memory can be utilized by the program for dynamic memory allocations. Now, let's see a system call called break and sbreak. As we have discussed earlier, break and sbreak are system calls on which library functions such as malloc, calloc, and realloc are built. But as a note, the user rarely uses system calls such as break or sbreak. Most of the time, the user uses the library functions such as malloc, calloc, and realloc. So understanding the break and sbreak will give us a good idea of how the dynamic memory allocation on heap works. In the syntax of break system call, we need to include unistd.h, and the syntax of break is as follows. It takes the new memory location in the heap area and it returns either success or failure. On success, it returns a 0. On failure, it returns -1. This points to the newly allocated memory location. For example, let's say that our current program break is at this point and we need a memory after the program break. So now the program break is being moved to the new memory location. As we have discussed, the break system call on success sets program break to the new memory location specified by the break system call. So whatever memory location we specify here, the program break advances to that memory location. After the program break has been advanced to that new memory location, the allocated bytes can be used for dynamic memory allocations, and the there is one more form of break, that is S break. The only difference between break and S break is, in S break, we specify the amount of memory that needs to be incremented from the reference program break. This means, for example, let's say that if we want to use S break here and we already have a program break pointing to the top of the memory where the memory can be allocated using S break, we have to specify the number of offset bytes we need to move the program break. So let's say we give a parameter as 10 bytes, then the program break advances by 10 bytes based on the system call. On failure, it returns a -1, which is typecasted to void star, and it sets a error number, which is a global parameter to ENOMEM, which means system is out of memory. And in case of success, it returns the pointer to newly allocated memory where the program break has advanced. Now let's see the malloc library function call. Malloc is a library function call where break and sbreak are the system calls. In general, C program uses malloc family of functions to allocate and deallocate memory on the heap. These functions are built over break and sbreak as we have discussed earlier. In the syntax of malloc, we have to include stdlib.h and we have to specify the number of bytes that needs to be allocated, and it returns a pointer typecasted to void star which points to the memory location where memory is allocated. In case of malloc has failed, it returns a null. Now let's see the next function, calloc. The calloc syntax is shown here. In calloc, we specify the size of block and number of times the size needs to be allocated. For example, let's say we want a memory for 10 integers. Then we have to mention size of int and how many such integers we need. This is a very generic syntax which can be used to allocate different types of data types. For example, let's say we have a structure with different data elements in it. Then we have to specify the size of one structure followed by number of such structural elements we need. So for example, size of one structure into 10 allocates total 10 such structures and provides us the pointer to memory allocated. The only difference between malloc and calloc is, in case of malloc, it allocates the memory, but it does not assign any value to the allocated memory, whereas in calloc, the entire allocated memory is filled with 0. Now, let's see the next set of function, that is realloc. In order to use realloc, we need to include stdlib.h, and realloc is used when, let's say, we already have allocated some bytes of memory, but during the execution we have found that the dynamically allocated memory size may alter, meaning it may increase or it may decrease. So in this case, we can make use of realloc to resize the memory previously allocated using malloc or calloc. In realloc, we specify the pointer that we have got previously by malloc or calloc, and we specify the new size that is required. Realloc in turn returns pointer to the allocated memory on success or null pointer on error. In case we are increasing the size of the block of memory, realloc attempts to form a single block. As we have discussed, memory allocations gives a contiguous set of memory on the heap. If the block lies at the end of the heap, then realloc expands the heap. If the block of memory lies in middle of the heap, then there is insufficient free space immediately following it. Realloc allocates a new block of memory and copies all the existing data from old block to the new block. So this is the case where the allocated memory is in between the heap and when the new memory needs to be increased. In this case, it cannot be increased by just adding some more bytes because there are other allocated memory. So in this case, a new set of memory is allocated on the heap. And the old memory contents are copied onto the newly allocated memory and it returns the pointer to the newly allocated memory. In this case, K must be taken as the old memory location and the newly allocated memory location may not be the same. Hence, storing memory address before reallocate and later using the same memory after realloc may give wrong results. Let us continue our discussion on memory allocation in Linux systems. When the dynamically allocated memory is utilized and we no more require the allocated memory, we need to explicitly free the memory. In order to free the memory, we need to use free function call. In free function, we pass the pointer to the previously dynamically allocated memory using malloc or calloc or realloc and free function frees the memory. So once the chunk of memory is freed, we cannot use it for any further memory operations. All the memory that is allocated using malloc or calloc or realloc needs to be freed. As an important note, the free does not lower the program break. It adds the freed block of memory to the list of free blocks. This free block can be used for future dynamic memory allocation calls. The block of memory being freed can be in the middle of the heap rather than the end of the heap. So lowering the program break is not done during free. Now let us discuss one more library function called as allocate. Until now we have seen that dynamically memory is allocated on the heap. Now there is a function call called as allocate which does dynamic memory allocation, but this memory segment is not allocated on heap. Rather, it is allocated on the stack of the corresponding function. Let's see the syntax of allocate. Here we need to pass the number of bytes required and it returns the memory location of the allocated memory on the stack. Let us say we call a function and in that function we need to do some dynamic memory allocation, and instead of malloc or calloc, if we call allocate, the required memory bytes will be allocated on the stack frame of the function, and after performing the required operation, the function returns and this will delete the stack frame. Hence, freeing is not required as compared to the dynamically allocated memory such as malloc or calloc. But care needs to be taken when using allocate as we may run into issues of stack as if we allocate more memory onto the stack grows and it may cause stack overflow. We have to use allocate only if the memory allocation is very small or when it is safe to use other allocations such as malloc or calloc. Now we will have a small look into the manual pages of the function calls that we have discussed. Let's refer to the manual pages. These are the below commands we need to type on the terminal. For manual page of break, we have man to brk. Similarly, for sbreak, we have man to followed by sbrk, and for malloc we have man followed by malloc. Similarly, for calloc, realloc and allocate we can use the manual pages. Now let's have a small glance of these manual pages so that it will be of useful for us. I would recommend to further read these manual pages to get a good understanding of the system calls and library functions that we have discussed. man to brk displays the manual pages of break, and it explains how to use the break system call. We can refer to the description. It's include file required for brk here. Now let's open sbrk manual page, man to sbrk. We can refer to the description. It's include files required for sbrk here. Then we have manual pages of malloc, calloc, realloc and free in the same page. So this gives a good description of how to use malloc, calloc, realloc and free. I would recommend to have a glance in the manual pages for more details on these function calls. In this video session, let's discuss a few examples related to dynamic memory allocations that we have discussed in previous video sessions. In this example, we are going to discuss the usage of malloc. Here, we included the required header file and we have taken a pointer to an integer and assigned it to null initially. And we have taken a count of 10. In this case, we are going to allocate dynamic memory using malloc. Meanwhile, let's see the syntax of malloc using man page. So in the syntax of malloc, it takes size underscore t and returns 1 star. Now let's say we want memory of 10 integers, then we have to mention size of integer into 10. This gives dynamically allocated memory in the heap for 10 integers. Since malloc returns void star, that is pointer to void, we need to typecast this void star into the required data type, that is integer pointer in our case, and assign it to integer pointer variable. Now if malloc fails, we get p_int equal to null and we print the message and exit the program. If malloc is success, we print the success result and then we assign required values to the dynamically allocated memory and then print the value that we have assigned. And finally, once the memory allocation is being utilized, we have to free the memory. So during free, we have to pass the pointer that is obtained by dynamic memory allocation. In this case, p_int points to the dynamically allocated memory and we need to free the same using free. Let's compile this program and run it to see the result. malloc.c is the name of the file. Let's compile it. gcc malloc.c -o malloc. Here we have created a object file called as malloc. Let's run this. Here we are getting malloc has successfully allocated memory and we have assigned some values and we are displaying some values using printf function. So in this case, we have assigned the integer 0 to 9 with a count 0 to 9 and we are printing the same using the next for loop. We have obtained the expected result here. Now in the next example, let's discuss calloc. In calloc also, we need to include the header files that is required for malloc. And in this case, we are going to take a structure named user and we have type defined it to user as shown in the code. Before using calloc, let's open the manual pages of calloc. In case of calloc, we need to pass two parameters. One is nmem and next is the size. So here we take a pointer variable to this user structure and assign it to null initially. Let's say we want 10 such structures allocated dynamically. So we use calloc in this case, calloc of 10 numbers followed by size of one user structure. Calloc now dynamically allocates memory on heap and returns 10 such structures. The memory location returns a void star. Here we need to typecast it to the required data type. In this case, we have to typecast the return of calloc to user star, which is nothing but the pointer to this structure, and we are storing in pointer variable puser. If calloc fails, we get the pointer variable puser equal to null, and we print the same and exit the code. In case of calloc, all the bytes that is obtained is assigned to 0 internally, but in case of malloc, it does not assign the allocated memory to 0. So here we print when calloc is success, and then we loop 10 times here and we store the ID and salary. Let's say we have salary and ID as a data elements of the structure, and we store some random values as shown in the loop. After that, we again print back the ID and salary of the structure from dynamically allocated memory using the loop. Finally, we free the pointer variable puser using free. Let's compile this program now. gcc calloc.c -o calloc. Now let's run this. We get the success message. Here we have 10 structures, and for each structure we are assigning the incremental ID starting from 0 and salary in increment of 1. So we have ID of 0 has salary equals to 100, and ID of 1 has salary equals to 101, and so on. So this is what we have assigned here, and we are getting the same using one more for loop. And finally, we have freed the dynamically allocated memory. One important point is the difference between malloc and calloc is, in malloc a single pointer is taken, a single parameter is taken, whereas in calloc it has two parameters. One is the size of the data type and other is how many such data type is required. Now let's go to the next example and discuss realloc. Let's see its syntax first. In realloc, whenever we get the memory allocation used during malloc or calloc, this pointer is passed here and the new size is being specified in realloc. So the realloc function reallocates the already allocated memory and returns the pointer. This returned pointer may be same or different from the original pointer. The same we had discussed in previous video session also. Now let's see the program. Here we include the required header files. Let's say that initially we had performed the malloc of 10 integers and assigned it to pint, where pint is a pointer to integer. And in the same way, if pint is equal to null, we say malloc has failed and we exit. With malloc success, we are again assigning some value to the newly allocated memory. Now let's say at some point of time we want to increase the allocated memory without changing the older values stored. Here in this case we use realloc and we pass the same pointer that we have obtained during malloc, and then let's assume we want a new memory of size 15 integers. So initially we had 10 integers, now we need 15 integers. Using realloc, we can resize the allocate memory. We can resize the allocated memory. In the same way, if realloc returns null, then we say realloc has failed and we exit the program. If realloc is success, we get the reallocated memory. Now in a loop of 0 to 15, we are assigning some values and then we are displaying the same. Let's compile this program. gcc realloc.c -o realloc. Now let's run this. If you see here, initially we had 10 bytes of dynamically allocated memory. Now here we have 15 bytes of dynamically allocated memory. Now let's say that we want to alter only the newly obtained memory that we obtained using realloc, that is from 10th memory to the 15th memory. Previously we had allocated from 0 to 9. So now let's provide values from 10 to 15 and then see the final results. Let's see the result again. I am recompiling the code again. Let's run the program. So if you see here, this is the old allocated memory values got by malloc, and these values are not altered. But after realloc, we have assigned only the new allocated memory, but the old value is unchanged. As a summary, we have until now discussed malloc, calloc, realloc and free. These are the function calls built using brk and sbrk system calls, and dynamic memory is allocated on heap. Thank you for joining this session.